So here we are talking about metal reactivity. This is forming the last little bit on what we need to understand for redox for this Unit 1-2 component. Okay, we'll look at an application of redox through corrosion, but the details of what we need to know in terms of our explicit content is ending here with metal reactivity. So let's have a look. Again, we have some objectives for these which link to our chapter. Remember when we're looking at chapter 16, this is that we need to understand that metals and halides have varying reactivities. Our focus here is on the reactivity of metals. Okay, I'm going to mention halogens and halides just because it gives us a better understanding, but our focus is on metals. We need to know that a more reactive metal is a stronger reductant and that a more reactive halogen is a stronger oxidant. Okay, so remembering that the reductant is the one that causes reduction to occur, okay, and is therefore oxidized. Okay, metals will oxidize to go from neutral metals to positive ions. They lose that electron. And we're going to look at being able to use experimental data to determine reactivity, looking at single displacement reactions. Okay, so those single displacement reactions. And that we're going to learn to use a reactivity series to predict the products between metals and ionic solutions. And this reactivity series is, of course, given to you in your tests if we expect you to use it. So looking at metal reactivity specifically, metals we know exhibit many common properties. And remember this from bonding. They're lustrous, they're ductile. Okay, they have a metallic lattice with a delocalized sea of electrons. One of the properties that we weren't able to explain using the metallic bonding model is the variation we see in metal reactivity. Okay, this idea that some metals don't react with oxygen or water in the air very quickly, while others seem to have quite explosive reactions like cesium. So when we define metal reactivity, we're looking at the reaction with water. Okay, so adding a piece of metal like sodium metal into water. Okay, and what happens when this occurs? We can also look at it with the reaction of oxygen and acids, but the more reactive the metal, the more reactive this equation is going to be. Okay, so if we remember back to the periodic table, we saw that the reactivity of metals can follow periodic trends, and you may remember that this trend, okay, if we have our periodic table, group 1, group 2, skipping across the middle, and then our P block, so we've got group 1, group 2, our D block transition metals, 13, 14, 15, 16, 17, and then our noble gases over here. Okay, so metal reactivity, you may remember, increases down a group. Okay, so they're more reactive down here where we have cesium and francium, and decreases as we move from left to right. And that makes sense because we start with metals on our left-hand side, and as we get over to the right-hand side, we're firmly in the non-metal territory. And it makes sense that non-metals will have less metal characteristics than metals. Okay, so we're remembering increases down a group and decreases from left to right. This means that our group 1 metals are going to be our most reactive. And if you remember back to sodium, okay, so sodium is kept under oil because it reacts quite violently with water. All our group 1 metals do. Group 2 magnesium corrodes quite quickly, and you'll remember back to our experiment with magnesium forming magnesium oxide. We just needed to put in a bit of heat, and we changed that shiny metal into a white powder through oxidation. That's actually an oxidation reaction. Iron, this is where we see rust on anything made of steel. So steel contains a large amount of iron. That iron will readily react with oxygen and form rust. Okay, which is the specific name we give to the oxidation of iron itself. Whereas if we look at things like copper and gold, copper is used extensively through wires in our house to carry electrical current. It's shiny and gold, you may have seen it. We use it on pots and pans. It has a wide variety of uses within our homes, but it tends to stay quite shiny. It might need a little bit of polishing every now and then, but copper and gold and silver are actually found, they're not very reactive, and they can be found in nature as the pure metals or easily smeltable ores. Okay, gold especially. This is a picture of a gold nugget. During the gold rush, people were actually just picking up chunks of gold out of the Earth's crust. And this is because gold is a very unreactive metal. So we find it in that lustrous metallic form that we associate with metals. Okay, whereas a lot of other metals are found as ores. So iron ore that we learnt about in Unit 1 and that need to be smelted. So group 1 and 2 metals are known as the alkali metals and the alkali earth metals. These we react with water to produce hydrogen gas and a metal hydroxide. Okay, so if this picture here, we have potassium and water. Potassium and water is going to produce hydrogen gas and potassium hydroxide. Okay, so this reaction, okay, so this reaction here is going to make the solution basic, okay, which is why they're known as alkali metals. We'll produce this hydroxide. And the production of the hydrogen gas, it's highly exothermic, as it does that hydrogen ignites, which is where we see the explosive nature of these metals. Okay, so group 2 metals, however, react with water. These are typically slower because they're not as reactive. They don't react with as fast a rate. The transition metals are generally less reactive than group 1 and 2, these because of their unique electron configurations, and we can go back to the electron configurations of these things like chromium and copper that show us that. Okay, so they're found in their pure elemental form traditionally, our transition metals, because they are less reactive. If we have a look at this, and we're going to look at some videos of these reactions a little bit later on, we can see that the reactivity with acids is another way for us to be able to identify the differences between these metals. So metals, when they react with acids, the reaction, because there's free H+, okay, is generally greater than that with water. A greater number of the metals will react with acids than with just water, and the reaction is generally more vigorous. Okay, so if we have a look at this picture here, we can see the reaction between magnesium, iron, so this is magnesium, this is iron, and then copper here. We can see that the magnesium is reacting readily. We have the formation of a lot of gas. We have lots of bubbles that are being formed here, and we can see that we have rapid formation of bubbles here that are bubbling right through the solution. With the iron, the rate of this reaction is obviously lower. We have less bubbles being formed. Okay, we would expect that this test tube is probably not getting as hot as this one either. And in the copper, we can see there's only a few bubbles. So the more reactive the metal, the more vigorous or faster this reaction will occur. Okay, so it's useful for chemists to use and predict how metals will behave or elements will behave using a reactivity series. And over here is an example of a reactivity series, and we're told that increasing reactivity. We have platinum down here, which is considered to be one of our most inert metals and is often used in high-end electronics and different applications, including electrodes for very sensitive reactions. Gold, silver, copper, these are all the ones that we tend to know of as jewelry. Okay, so if you can wear it on your skin without it burning your skin or reacting harshly, it's probably going to be a non-reactive metal. Okay, if you think about it, we don't want to put reactive metals on our skin. If they're going to react exothermically with the environment, that's going to hurt. Then as we go, we have increasing reactivity. Lead used to be used in pipes. Iron we use in construction. Zinc, aluminium, magnesium, calcium, sodium, and potassium. Here we are with group 1. And here we are with group 2. Okay, so we can see this reactivity series here. So very few metals are found in the Earth's crust as pure elements, like gold is an unusual metal for this, generally because of their reactivity with water, but also oxygen in the atmosphere. They form different crystalline ionic compounds. Okay, these ionic compounds, of course, are going to be the ores that we get pure metals from. Okay, so this is what we tend to mine. When we say we're mining aluminium, we're actually tending to mine bauxite and then processing it into aluminium. These metal oxides undergo a large amount of processing. Only gold and platinum and a few others are found in the Earth's crust as pure metals. When we move on to comparing our reactivity, okay, we can describe these comparisons by doing different reactions with water and looking at the observations that we have. Group 1 metals will tend to react vigorously or violently with water. Things like rubidium will react so quickly it will explode. Sodium reacts quickly, potassium more so. Group 2, magnesium doesn't react with water at room temperature, but it will react with steam. So if we give it a little bit more of a kick with temperature, we can see a reaction happen. Calcium reacts slowly with water at room temperature, remembering that calcium is lower down in the periodic table, so its metal reactivity is going to increase. So this is a reactivity series, okay, so most reactive at the top, least reactive at the bottom, and a table that summarizes whether or not they're going to react with dilute acid, oxygen, or water, and how easy or difficult they are to extract. These things all being dependent on their reactivity. Okay, so the more reactive it is, the more of these criteria it's going to meet. Okay, so if we look at comparing metal reactivity, this is where we get single displacement reactions. Okay, with single displacement reactions, the more reactive metal will displace the less reactive from solution. Now, this makes sense if we think about, in order for metals to react, they must lose electrons. Okay, they react in an oxidation process. They must lose electrons. They form positive ions. Okay, so that means that they need to be able to give away those electrons. So the more reactive metal is going to be more readily able to give away its electrons, and it will give them away to something that is a less strong reductant, okay, that is being forced to take those electrons. So if we have a look here, copper, of course, won't displace copper from metal, copper metal from solution. Copper is the least reactive in this list, so it is unable to displace any other ion. If we look at lead, lead is more reactive than copper, so it will displace copper from solution, which means that I will form Cu solid. Okay, here I will see a precipitate of Cu solid being formed, and lead will turn into Pb2 plus in solution. I won't see that happening. As we increase reactivity, we see that these metals will displace more from solution. So iron can displace copper, lead, and just copper and lead, and tin over here because it's more reactive than tin. Magnesium, it can displace copper, lead, iron. Of course, it can't displace itself, but it also displaces zinc and tin. Zinc can displace everything except itself and magnesium. And then tin can displace copper, lead, and those two. So from this, we can see where tin might fit in the reactivity series, in that tin is likely to fit in somewhere up here between lead and iron, because tin is able to displace lead, but it can't displace iron, so it would be between iron and lead in a reactivity series. So this is what we're talking about when we predict reactions. So let's have a look at each one of these. If I add iron, which is going to be Fe solid, into a solution of copper 2 sulfate, I'm going to have Cu2+. I'm going to look at my reactivity series. Here is copper, okay, and here is iron. Iron is more reactive than copper, so I will see copper forming on the iron rod. Copper will be deposited, and the iron will go into solution. Okay, let's have a look here. Copper and silver nitrate. Silver is less reactive than copper. Okay, so in this case, I will see, if I place this rod into this solution, I will see crystals of silver forming on the copper rod, and then over time the solution will turn blue as Cu2+ is dissolved into solution. Okay, gold and copper 2 sulfate, in this case gold is far less reactive than copper. Okay, so because gold is far less reactive than copper, I will displace the gold from solution, so the gold will precipitate out and the copper will form on, hang on, let's get that right. I am putting gold into copper solution, so the gold will not be able to displace the reaction. Okay, in this case, gold is less reactive than the copper ions, so it's not able to force its electrons onto the copper. Okay, copper is more reactive than silver, so it can, and iron is more reactive than copper, so it can. So, but this one we will see no reaction. Okay, because the gold is less reactive than the copper. If we look at zinc and iron 2 sulfate, the zinc is more reactive than the iron. Okay, so I will see iron being displaced from solution, and the zinc will oxidize and go into solution. Okay, this one's been going for a little bit of a while, so a quick note on halogen reactivity. Just like metal reactivity, halogens have varying reactivity. They increase as we go up a group, remembering that this is dependent on electronegativity. So halogens will also undergo displacement reactions. Okay, it's the opposite trend to metals. This is not something you need to worry about too much though. So that is what we have covered in this video, and that covers all our metal reactivity. The skills that you need to be able to do is to be able to compare reactivity of metals and use experimental data such as the reaction with acids and water to work out which ones are more reactive, and then predict metal displacement reactions, which is what we'll be doing in our skills practice. Good luck with that, and I'll see you in class.